In this lecture, I'm going to give an introduction to continuously compounded interest. Now, continuously compounded interest picks up from periodically compounded interest. Here's how that happens. So first, recall that this is the formula for periodically compounded interest. You have a principal amount P, that's the amount borrowed. You multiply by this thing, which is a bunch of periodic interest rate factors 1 plus r over n. And how many are there? Well, you multiply n, the number of compounding periods per year, by t. Now let me fast forward through the calculations here. Suppose I borrow $1,000 at an annual interest rate of 5%. What is the amount of debt after 4 years if the interest is compounded yearly, once a year, quarterly, 4 times a year, monthly, 12 times a year, or daily, which would be 365 times a year? The terms of the loan here are all the same except for the n, the number of compounding periods per year. As you look down this list, the number of compounding periods per year, n, increases. As it does so, the amount of the debt after 4 years also increases, but it's not increasing hugely. I mean, here we've gone from 12 to 365, and we've added less than $1. So it looks like that as the number of compounding periods per year increases, maybe these debt values are converging to something. Well, it turns out that they are. So let me skip this problem that we did before and go to this screen, continuously compounded interest. So here's the idea. We start with the formula for periodic compounding, and we look at what happens if we allow the number of compounding periods n to go to infinity. So this is a difficult limit to work out. I am not going to explain any more about how it actually works here. If you're interested in that, then you should take one of our real analysis courses. But the result is that the limit does exist, and it's equal to P times e to the RT. P is still the principal, the amount borrowed. R is still the annual interest rate expressed as a decimal. A is still the amount at a future time, the future value of the debt. T is still time in years, but this symbol E is a magic constant. It's a number that shows up all over the place in mathematics. It's just as important as pi, for example, and it's in fact very closely related to pi in a number of amazing ways that, again, I don't have time to get into. Take a complex analysis class and you'll see some great stuff linking E and pi. But it's defined, well, there's a number of ways to define it, but it happens to be equal to this particular limit. And you can see that this is not too different from what happens over here. And the value of this limit is 2.7 and some change. So if we want, we can, of course, remember this formula very easily because there's a brand of shampoo that goes like PERT. Now, let's go back to this problem. Suppose I borrow $1,000 at an annual interest rate of 5%. What is the amount of the debt after 4 years if interest is compounded according to, well, let's use continuous this time. So here's the calculator. The continuous compounding formula is that we multiply the principal, which is the same 1,000 that we did in previous exercises, times, and here I'm going to say more about this in a minute, but the symbol that we want to use is right here. Let me slide this up into the zoomed area. You can see it says e to the x right there. That's the best way to do the magic number e to a power. Then we multiply the interest rate expressed as a decimal, which for this problem is 5%, so 0.05 times, and the time t is 4 years. So now hit enter, and you can see the result there, $1,221.40. And that is not too different from what we were getting from periodic compounding. And again, just so that you can see this, here's the formula. The amount of the debt is P times e to the RT. And there's the calculation we did.